Hello. In this video I will be discussing a particular reaction of alkenes known as hydrohalogenation. It's generally the one that's started with when one learns about the various reactions of alkenes. We will be eventually learning 11 reactions of alkenes. We will be eventually learning 10 reactions of alkenes. They are just quickly hydrohalogenation. It's the one we're going to be discussing in detail in this video. But then also there's a reaction called hydration, one called halogenation, one called halohydrin formation, one called oxymercuration demercuration, another one called hydroboration oxidation, another one called diol formation, one called hydrogenation, one called epoxidation, and one called ozonolysis. That sounds very intimidating, but we will learn each one of them in turn, and those names will make sense to you as we discuss those reactions. But in this video, I'm going to discuss the single one of those 10, known as hydrohalogenation. It's a fairly simple reaction, and we will spend some time in this video talking about the details of that reaction, because they will be similar in some ways and different in some ways to similar types of things in others of those 10 reactions, so that if you get the ideas down in the hydrohalogenation reaction, it'll make it easier for you to learn those same kinds of details in the other reactions. So what does hydrohalogenation refer to? Well, it's generally a reaction of alkenes. I'm going to draw a generic reaction scheme here. Generic meaning that it is not a specific alkene reaction that we're starting with, but a general alkene. Notice that these four positions could be hydrogens or other carbon groups or some combination of hydrogens and carbon groups. And if there's carbon groups, they don't have to be the same as each other. So this could be any one of essentially any alkene that you could draw. And what we're going to do is, in a flask, we will take that alkene, generally dissolve it in some sort of a solvent, and we're going to add a molecule of HX. Now the X in this case stands for chlorine or bromine. So this reagent that we're using here is either hydrogen chloride or hydrogen bromide, generally not in the form of hydrochloric acid or hydrobromic acid, but often in the case of, generally that can be hydrochloric acid or hydrobromic acid, or sometimes it can be added directly as a gas rather than as a solution in water. In any case, remember that HX means HCl or HBr. They both work the same way, so we're going to use X as a generic symbol to stand for chlorine or bromine. You might wonder, could we use HF and could we use HI, since fluorine and iodine are both also in the same column with chlorine and bromine? The answer is they don't work as well, so generally we're just going to use HCl or HBr. And what's going to happen is pretty simple. The hydrogen and the chlorine or bromine will split up. One of them will attach to the carbon, the other one will attach to the other carbon, and the double bond will become a single bond. So here's the structure that we'll draw for the final product. We'll have the H on one of the two carbons and the X on the other carbon. Notice that this is a balanced equation, very simple reaction, very easy to remember. Just add hydrogen to one carbon, add chlorine or bromine to the other carbon, and you're done. So generally what we like to do when we're learning new reactions is classify what kind of compound do you get from each reaction. In this case, we start with an alkene, and we always end with what class of compounds is that. Well, generally what we call it when there's a halogen, that is chlorine or bromine, attached to a carbon group, we call it an alkyl halide. That's two words with a space in between, or also known as haloalkanes, all one word. So alkyl halides or haloalkanes, those both mean the same thing. This is sort of a common way of naming them. This is sort of an IUPAC way of naming them, but both of those terms mean the same thing. And again, they just mean a halogen with a carbon group attached. So the general category of compounds we get from this reaction is haloalkanes. By the way, this reaction has a name, and that's something you should keep in mind. Every organic reaction we will learn has to have some sort of a name. Sometimes they're official names, sometimes they're named after people, sometimes they're just, the name is sort of describes what happens in the reaction. So for example, this one is known as hydrohalogenation. Which seems like a mouthful to say, but really is descriptive of the reaction, because what are we adding onto the alkene? A hydrogen, thus the prefix hydro, and a halogen, thus the prefix halo, and then the ation is just a suffix that means this is the process that happens. So hydrohalogenation is the addition of hydrogen and halogen to a double bond. So there's the overall reaction. And this is again in what I refer to as a generic format, not being a specific alkene or a specific alkyl halide to finish up with. So let's just do a couple of examples here, and then we'll see where it can get a little bit more complicated than it seems at first. So I'm going to put a structure on the board and ask you to draw the product that you would expect to get if we were to actually do this in the laboratory. Okay, so here is a simple alkene. And you could name that, since you know how to name alkenes, you would, if you thought about it for a minute, call that 2-butene, because it's 4 carbons, double bond at the second of the 4 carbons, and so it's 2-butene. If we add HX, let's make it specific, let's add HCl to that molecule. By the way, I'm using a notation here that's a little bit different than the one I used a second ago. The one I had on the board a minute ago was a balanced equation, where we put everything that's being added on the left-hand side and everything that's being produced on the right-hand side. This is a shortcut notation that organic chemists use a lot. They'll just write the reagent over the arrow. Sometimes they'll also put other things over or under the arrow, like temperatures, solvents, times. They'll even say 2 hours or 5 hours or however long it takes the reaction to happen. So the arrow sort of serves as a dumping ground for an organic chemist to put anything up on the board that he or she thinks is important to the reaction conditions. In this case, we're just going to put the reagent over the arrow, and then I'm going to have you draw the structure of the product that you would get over there. So take just a minute and see if you can draw what you think the product would be in that case. Okay, let's do it. What we're going to do is take the CH3, the CH single bond now, CH, CH3, and we make it into a single bond because we need room to add the hydrogen and the halogen. One of the carbons is going to get the halogen, let's put it here, and one of them is going to get the hydrogen, so let's make that a CH2. So notice that the CH has become a CH2 because we have the hydrogen there. This CH has become a CH with a chlorine attached. Excuse me, that should be chlorine. Specifically because we're adding HCl. And that's the product that we would expect to get. So a chemist would take some 2-butene, mix some HCl with it, shake it up, perhaps heat it. We're not worried too much about the details of what you would have to do in the laboratory to make this happen. But in one way or another, the chemist would then isolate this product out and would somehow identify it as being that compound. By the way, anybody want to make a stab at naming that compound? I'll tell you what it is. You can probably figure this out for yourself. Sec-butyl chloride is the name of that compound. Okay. You might want to take a minute and see if you can figure out why it's named that. We won't worry about naming alkyl halides just yet, but I think you can see it's not that complicated. Okay, one detail of this reaction that you may have noticed is the 2 carbons of this particular alkene are the same as each other, so it doesn't matter whether we have the hydrogen here and the chlorine here, or vice versa. Some of you may have put the chlorine here and the hydrogen here, which of course is fine because it's the same product. It's still sec-butyl chloride, but that won't always be the case. So it becomes a little more complicated if we have an alkene like that one, in which the 2 carbons of the alkene are not the same as each other. Now it does matter which one of these is going to get the hydrogen and which one of them is going to get the halogen. Just to change things up a little bit, let's make it HBr. And let's see if we can predict what the product is going to be. Now you've probably tumbled upon the fact already, if you thought about it for a minute, that you don't know, is the bromine going to go here and the hydrogen there, in which case we get one particular product. In fact, let's write them both out. If we put the hydrogen in one place, like on that carbon, so that becomes a CH, this becomes a single bond. The CH picks up the bromine, and the CH3 is still there. That's a possible product. And the other possible product is putting the bromine on that one, and the hydrogen on this one, so that the CH becomes a CH2. Are those the same product as each other? No, they are not. This one is clearly different from this one because in this one the bromine's attached to a tertiary carbon, in this one the bromine's attached to a secondary carbon. So what is the situation in real life? If we were to do this in the laboratory and isolate the product here, would it be this one, or would it be that one, or would it be a mixture of the two? The fact is it probably would be a mixture of the two, but the vast majority of it is going to be this product. Okay. Now, I would expect you to be able to predict that. So is there a rule to help us predict that kind of thing? And the answer is yes, there is. There was a man in Russia named Markovnikov. Write his name here. I'm going to point the arrow at that product. Markovnikov is how he spelled his name. And he worked on reactions in which HCl and HBr were added to alkenes. He just tried lots and lots and lots of different alkenes to see if he could come up with a rule. And what his rule was, he came up with them that has gets. Meaning, whichever carbon of the two carbons of the double bond has the most hydrogens already, that's the one that's going to get the new hydrogen. So notice this carbon doesn't have any hydrogens already, and so it ends up not getting the new hydrogen. Instead it gets the bromine. This carbon has one hydrogen already. It ends up getting the new hydrogen and becomes CH2. So this refers to hydrogens. The one that has the most hydrogens already ends up getting the new hydrogen. Okay. So now we have a rule. It's called Markovnikov's rule, and it will help you predict what the product would be in most cases if the two carbons of the double bond are different from each other. Now there are some cases where Markovnikov's rule won't help us because you may end up with a molecule that, you may start with an alkene molecule that has the same number of hydrogens on both carbons, but still they are different from each other in one way or another. In that case then Markovnikov won't predict which one's the major product and you'll end up with both. I won't give you an example of that right here, but I would strongly urge you to see if you can come up with an example like that yourself. That is an alkene to start with, in which the two carbons both have the same number of hydrogens, say one hydrogen on this one and one hydrogen on this one, but are different from each other because the two groups on the ends are different from each other. And see if you can draw the structures of both products and see if they are the same as each other, and notice that the Markovnikov rule won't help us in that case. So I'll leave that to you. But now that we have the Markovnikov rule, we'll be able to predict the major product in most cases. So let's do another example. Let's do a ring. What if we start with cyclohexene, in which we have a methyl group attached to the double bond on one of the two carbons, but not on the other carbon of the double bond. And let's add HCl to that molecule. I'll give you a minute and see if you can figure out what the structure would be. You might want to pause the video right now and work out, draw the structure of the product, and then restart the video and we'll reveal the answer. Welcome back. How are we going to do this problem? Well, we know that one of these two carbons has to pick up the hydrogen and the other one has to pick up the chlorine. The double bond will be gone. So let's write the skeleton of the molecule. Keep the CH3 there, but not put the double bond in. Now the main question is, where will the chlorine go? Well, remember the rule, them that has gets. How many hydrogens does this carbon have already to begin with? None. How many hydrogens does this carbon have to begin with? One. It's not shown there, but remember in these polygon figures, it's not always going to be shown. So this one has one hydrogen, this one doesn't have any hydrogens. The one that has the most hydrogens already is going to get the new hydrogen, so that becomes a CH2. You can draw in the two hydrogens there, or you can just leave it as an angle, which suggests two hydrogens there. But the important thing is that the chlorine is going to add on to the other carbon that doesn't have the hydrogen already. So we'll end up with a chlorine at that position. So there's the product that you should draw. If you want to, as I said, leave two hydrogens there, that's fine. Or if you want to just not show them, it's implied that those hydrogens are there. So that would be the product that you would predict for that particular reaction. Now I think you can probably predict in just about every case, if you start with an alkene and you add either HCl or HBr to it, you will be able to predict what the product is. And you should practice that with, just draw some alkenes and see what you come up with. The last thing we want to do in this video is talk a little bit about the mechanism of the reaction. We haven't done mechanisms yet, so this will serve as a guide for how to do mechanisms in general. And in future reactions that we'll learn, others in this particular chapter, for example, we will have mechanisms that we have to learn, and they'll follow the same general rules, although it won't be the same as this mechanism. So what do we mean by a mechanism? Well, you remember that a mechanism is a series of steps by which a chemical reaction occurs. Let's use propene as an example. I'm going to use a red pen here. Propene being a 3-carbon alkene, and let's add HBr to it. Now I suggest that when we're writing the overall reaction for the purposes of doing a mechanism, that we should write it as a balanced equation rather than using the little notation where we write things over the arrow. Let's put everything that goes into the reaction on the left, and let's put the product on the right. By the way, which carbon of these is going to get the hydrogen? Which one's going to get the bromine? Well, that one clearly has more hydrogens already, that being 2. So it's going to get the new hydrogen, it'll become a CH3. The bromine then will become attached to that carbon, and we'll end up with that molecule. So there's the overall reaction. It's always a good idea to have the overall reaction written as a balanced equation before you start to do a mechanism. Then what we do is write the steps by which each of the bonds that gets formed and each one gets broken, and why the various atoms go into the places they do. So in this mechanism that we're going to write now, we have to account for 3 things. We have to account for when does this carbon-bromine bond get formed, when does the carbon-hydrogen bond that gets formed in here, since that hydrogen ends up attached to that carbon, when does it get formed and how does the double bond turn into a single bond. So we'll be showing some electron pushing using curved arrows, and generally show exactly detail by detail how does the reaction occur. But here's the first step. In the first step, the alkene encounters the HBr. I'm going to write it as a balanced equation. Now, what do you suppose happens? Well, I'm going to tell you. And by the way, when you're learning mechanisms, you will memorize essentially the steps by which a mechanism happens. But I think it's really important, as I always tell you, to realize that if you understand why the steps happen the way they do, it makes it a whole lot easier to memorize the mechanisms. In fact, there are really very few different steps that you might see in a mechanism. It's just a matter of learning a few of them, and then you can put them together to make mechanisms. Well, in this first step, because HBr is a strong acid, it's going to give away an H+. So that's one thing you can think of if you're trying to memorize this step is, well, probably the HBr does what strong acids always do and gives away an H+. So it's going to attach an H+ on one or the other of these 2 carbons, and in the process it's going to become Br-. So Br- is actually formed in this first step. Where are we going to add the H+ onto? Well, we could add it onto here, and what we would do is use a pair of electrons from the double bond to form that new bond, but that would leave this carbon without an electron, and it would end up being positive, and we would end up putting the new hydrogen onto that carbon so it becomes CH3. At the same time, the double bond would disappear because one of those pairs of electrons had to be used to form the bond to the new hydrogen attached there. That then leaves this carbon lacking 1 electron, so it ends up being positive. What kind of, and so that's a carbocation, isn't it? It's carbon with 1 positive charge. What kind of carbocation is that? Well, how many carbons attached to this carbon with a positive charge? 1, 2. So it is secondary. Notice that this is a secondary carbocation. Why is it secondary? Or why Why does it do that? Because the other possibility is, of course, that this hydrogen could attach onto that carbon, and it could become CH2 using one of the pairs of electrons from the double bond. That would leave this carbon without its electron, and it would end up being positive. Imagine, and write it down if you want to, what would that, if we ended up with a positive charge on that carbon, would it be primary, secondary, or tertiary? What do you think? The answer is primary. And since secondary carbocations are better, as we learned in the previous video, then primary secondaries are more stable. Therefore, it's the secondary carbocation that gets formed rather than the primary one. And notice, little preview here, that's where the bromine is going to end up being attached to. So that's why the bromine ends up being attached to the other carbon, and the one that has the most hydrogens already is the one that gets the new hydrogen. It's because of the stability of carbocations. Markovnikov didn't know that. He didn't know anything about the mechanism. He just did a bunch of reactions and tried to figure out the pattern from looking at what actually formed. Anyway, that's the first step in the mechanism. Very simple. It's really just an acid-base reaction in which this X is the acid, this X is the base, this is the conjugate base, and this is the conjugate acid. In the second step in the mechanism, the carbocation that we just formed, floating around there in the solution, it encounters a Br minus. Maybe the Br minus that was ejected from the HBr in the first place, or maybe it's a different Br minus that got ejected from a different HBr. Doesn't really matter, because the fact is it's going to find the Br minus floating around, and it's going to, one of the pairs of electrons from the bromine, let's put 4 pairs of electrons on there because that's really what Br minus is going to encounter the positive charge. That positive charge is very electron efficient. It wants to find electrons if it can. It finds a big fat pair of electrons on the bromide and says, okay, I'm going to borrow that pair. Well, the bromine says, you're not going to take it away from me, let's share it. So it forms a bond with the positive charge. In the process, of course, that neutralizes the positive charge on the carbon because now it has 4 bonds, just like it wants to. It has its octet. And that neutralizes the negative charge on bromine because now it has its 7 valence electrons, which is what bromine's supposed to have. So everything is happy, and we are done with the mechanism. It's a very simple 2-step mechanism. First, you protonate the double bond. By the way, let's talk about that word protonate. That's a jargon term, and we've mentioned it before, but just to repeat, protonate means to put a proton on, and a proton is a jargon term that chemists use to mean H+. So protonate has a little word proton in it, refers to an H+ attaching to something. Notice, if you will, nowhere in this mechanism is there a free H+. There's no such thing as H+. The H+ is attached to the bromine in this, on the left-hand side of the arrow. It's now attached to the carbon on the right-hand side of the arrow. It was transferred from the bromine to the carbon, but never had free existence in itself. Nevertheless, we use the term protonate to mean as if it were a proton that we're somehow attaching onto the carbon. So the first step is a simple protonation. The next step is a simple bond formation between a positive and a negative charge. Here's another little detail you might be interested in. The second step is also an acid-base reaction, but it's a Lewis acid-base reaction. So you might want to go back and review quickly what is a Lewis acid-base reaction, and you'll find, once you think it through, that this carbon is a Lewis acid, this bromine is a Lewis base, the Lewis base is donating a pair of electrons to the Lewis acid, and it produces a bond. So this is actually a Bronson-Lowry acid-base step, this is a Lewis acid-base step. And what we'll find when we're doing mechanisms of reactions in general is that many of the steps that we will learn in various mechanisms of all sorts over the course of the semester, many of them can be categorized, if you look carefully at the reactions, as acid-base reactions, either Bronson-Lowry like this, or Lewis like that. Okay, we're done with that mechanism. One other thing we should talk about in terms of mechanisms, well, a couple of other things. In general, I see over and over and over again people making mistakes when they do mechanisms of a variety of types. One is you have to make sure that your equations that you're writing in your mechanism, in this case there's just 2, are balanced equations. So if there's 3 carbons on this side, there has to be 3 carbons on this side. If there's a total of 8 hydrogens on this side, there has to be a total of 8 hydrogens on that side. I guess it's actually 7. 1, 2, 3, 4, 5, 6, 7. So 7 hydrogens on this side, 7 hydrogens on this side. 1 bromine on this side, 1 bromine on that side. But even more important, well, I shouldn't say more important, but just as important is charge. Make sure you're not creating new negative charges or positive charges that weren't there to begin with. So let's note, what is the net charge on the left-hand side of this first reaction? 0. No positive or negative charge on either one of those things. What's the net charge on the right-hand side of the equation? Positive charge there, negative charge there. So again, net 0 charge. We haven't created or destroyed any positive or negative charges. That's really important. And it's so easy to do that it seems like you shouldn't make that mistake, but people will make it all the time. So just quickly, every time you write a mechanism step, make sure that your charges are balanced. What about down here? Is it a balanced equation? Yep, 3 carbons, 7 hydrogens, 1 bromine, 1 bromine, a net, 1 positive and 1 negative for a net 0 charge on that side. No charges at all for a net 0 charge on that side. Again, the charge is balanced and it's a good mechanism step. And then finally, let's remind ourselves that when you write a mechanism, you can add up the steps of the mechanism and it should add up to the overall reaction. So let's draw a line under here. And let's cancel out anything that appears on both sides of the mechanism. What appears on both sides here? Well, notice that the CH3 with a positive charge, that cancels out because it's on the right-hand side in the first step and it's on the left-hand side in the second step. So that we can cancel out. That's what's known as an intermediate because it gets formed in the first step and then it gets used up right away. Well, that's good because carbocations, as we learned in the previous video, are not very stable at all. You can't keep them in a bottle. They don't last for more than a millisecond at the most. So it gets formed and then immediately gets used up again. So it doesn't appear in the overall balanced equation because as soon as it's formed, it gets used up. Is there anything else we can cancel here? Yes, we can cancel the bromide. Notice that the Br minus occurs on the left-hand side and on the right-hand side. So we can cancel it. Does that mean it's also an intermediate? Well, sort of. It's not unstable, so we could have bromide in a bottle, say sodium bromide, but it turns out in this case it gets formed at the same time this gets formed, and then it gets used up at the same time this gets used up. In fact, it's really the counterion for that positive charge in both cases. So when one gets formed, the other one gets formed. When one gets used up, the other one gets used up. And then what's left over? What's left over is the propylene on the left-hand side. There it is. The HBr on the left-hand side, there it is, and the isopropyl bromide on the right-hand side, there it is. And so everything that doesn't get canceled out can be brought down and written as a complete equation, and what you'll see is that the overall reaction is the same as the sum of these two mechanism steps. If that doesn't work for your mechanism that you're writing, then you know you've made a mistake somewhere because the individual mechanism steps have to be balanced equations in themselves, and they have to add up to the overall balanced equation that you've written as the overall reaction. Thank you for listening, and we'll see you next time.